Let's look at how we can calculate distance, for instance. Here we have a blindfolded geoscientist who wants to know how far away a wall is. By having him use only his ability to hear these sound waves, let's see how he can figure out how far away that wall is. When listening to human speech with normal hearing, you do not have to face the speaker. He can have his back to you, and yet you can hear what he is saying. How? In the room, the sound waves created by his voice bounce off the wall, the ceiling, the floor. These waves reflect back into your ears. We call these waves that bounce back reflective waves. To measure them, we calculate the time it takes for a wave to get to the wall and then reflect back. We call this two-way travel time, or TWTT. Before I go on, I want to show you this example. Notice that some of the waves continue downward and some of them come back. The sound waves that do not bounce back but continue traveling out from the source through air, water, walls, whatever, are called refractive waves. When we create waves, we create refractive waves that continue on and reflective waves that after hitting a boundary bounce back. Both of these types of waves are used to help determine the properties of rock like density, elasticity, porosity, and saturation. Now going back to the blindfolded geoscientist, he still needs to know how far away the wall is. To find out, he will need an energy source, a timing device, and a receiver. We begin by creating an energy wave. He shoots off his energy wave, and using a receiver with a timing device, he can now get the time and calculate how long it took for the wave to travel to the wall, reflect off of it, and travel back. He can measure the sound wave's two-way travel time, TWTT. He records that the TWTT is 0.1 second. Now, knowing the exact travel time, he can calculate the distance. From physics, he knows that the sound travels through an environment of standard temperature and pressure at a velocity of 347 meters per second. By using this formula and knowing that capital D equals one-way travel time and small d equals two-way travel time, we can write distance is equal to velocity multiplied by the time, or d equals v times t. To calculate TWTT, we write little d equals v times t divided by 2. The blindfolded geoscientist figures how far away the wall is. Remember, he measures the time it took for the sound wave to travel to the wall and back. If he only wants to measure the time it took for the sound wave to travel just to the wall, then he must divide the travel time by 2. Therefore, putting his numbers into the formula, he writes d equals velocity times time divided by 2 equals 347 meters per second times 0.1 second divided by 2 equals 17.35 meters. The blindfolded geoscientist now knows he is 17.35 meters from the wall. This is the basis of seismic. Measuring the time it takes for sound waves to travel to a boundary and back, we can measure height, width, and depth. Understanding how to interpret these measurements of simple sound waves gives us eyes to see into the subsurface. Now let's apply this concept to help us decide where to drill our first wildcat well. In this drawing, I have placed my sound receiver, geophone, if on land, and hydrophone if offshore. When I fire the gun, sound waves created by the detonation flow out in a circle or radial direction. The ray of interest is the wave that takes the shortest, most direct path. Using my geophone or hydrophone, I record the reflected wave as it returns to the surface. By closely timing the reflected rays TWTT, I can calculate the exact amount of time the wave's journey takes. The refraction wave continues downward and outward, creating another reflective wave when it detects another boundary, because it too is influenced by the density, elasticity, porosity, and saturation of the matter it travels through. My geophones and hydrophones allow me to accurately record all of these reflected waves' travel times, and from these I can deduce what is in the subsurface. Each reflection that comes back will represent another layer or boundary of where rock type changes. Let's look at an actual example of using seismic technology. Here we have a ship out in the ocean doing seismic work. The first challenge for the geoscientists is to find the depth of the water. Let's look at how they can calculate the depth using seismic. First, the geoscientists calculate the velocity of a sound wave in water, and then they will use the velocity calculation to determine how deep the water is under our ship. They place their air gun at this point on the surface of the water. Next, they place the last sound receiver on this string at a precise location of 1,000 meters away from the gun. Then the gun is fired, creating a sound wave. This wave travels in a radial direction. Now they measure the length of time that this part of the wave takes to travel through the water from the gun to the last hydrophone. Because they measured it, they already know that the distance from the gun to the hydrophone is 1,000 meters. Their timing device reports that the travel time was 0.6757 seconds. They insert these numbers in their formula. Capital D equals V times T, or D equals 1,000 meters equals V times 0.6757 seconds. Solving for V, we rewrite the formula as V equals capital D over T, or V equals 1,000 meters divided by 0.6757 seconds. We calculate that V is 1,480 meters per second. Note that this is only one-way travel time. We are measuring only the time it took the wave to travel from the gun to the hydrophone. We now know the velocity of this direct wave traveling through water is 1,480 meters per second. The measurement of this yellow direct wave is one-way travel time because it did not reflect back. It did not bounce off of any boundaries. The direct wave traveled straight from the gun to the hydrophone.